Okay, now, today is January 10th, 2013, and we're just talking about I, which is known as the square root of -1. I is the culmination of a couple things in math that have frustrated me on and off since I was, no lie, about 11 or 12 years old. I never truly accepted, just on faith, that a negative times a negative would really equal a positive. Bothered me. When I taught middle school, I came up with some explanations on my own of why, thinking of negative in terms of direction. Turns out I was closer than I thought. Eventually, in a math history book, I found out where people came up with this. And it frustrated me. I knew some very smart math teachers. A great math teacher I knew when I lived out west actually said, mathematicians didn't know what to do with the square root of -1, so they just threw it on this perpendicular axis. Now, in Algebra 2, I know you talked about the square root of -1. It just occurred to me as I said that. I'm not sure that every Algebra 2 class got to discussing something called the complex plane. And the good. The complex plane, horizontally, it's just like the Cartesian coordinate plane that you're used to. This week, you've gone from looking at one plane in math to 3. We've talked about polar, now we're talking complex. We'll start mixing them soon. You've got an x and a negative x. This is not y and negative y, though. This is positive I square roots of -1. This is negative I. Now, what horrible timing. Okay. So this complex plane gives a little context to my last statement, which was just that. So a very good math teacher I knew, fantastic guy, very smart, but he just said mathematicians didn't know what to do with these square roots of -1, so they just threw them perpendicular to a number line. It's not true. This has to look like this. It must. I'm going to tell you why. Go back about 300, 400, 500 years, the idea of negative numbers is very controversial. Kind of more controversial then than the square root of -1 is today. What could a negative number mean? How could you have a negative of anything? I mean, these people were very smart and sophisticated. They understood things like debt. But debt was just positive money that you owed someone. It just went in a different column. It wasn't negative. There weren't submarines, so why should you care about below sea level? There was no uniform set of guidelines for temperature. There was no set temperature scale. So what would below freezing mean? Why would they need negative numbers? What could they possibly mean? But some mathematicians started seeing a use for them. They didn't originally like the negative notation. Some people fought against it. They liked to think in vectors. So they like to think in terms of direction. So picture this. You've got your positive counting numbers. That is going to get irritating quickly. You've got your positive counting numbers. 1, 2, 3, 4. If you're going to introduce a negative idea, it was originally introduced and still today means the idea of direction. So these numbers can no longer just be represented by one idea. This has to be 1, 0 degrees. This, for example, has to be 3, 0 degrees. Keeping in mind with the unit circle that horizontal and to the right is 0 degrees. It doesn't have to be that way, but that is the way that makes all those nice trajectory equations you learned in physics work nicely. If this is +1, 0 degrees, and negative numbers have not been invented yet, then what's that? We can go ahead and use the Sumerians. We're not in radians yet. We can use degrees. That's not a negative. 1 what? 1, 180 degrees. There is no negative number yet. That hasn't been invented. There's just positive distances from 0 left and right in this one-dimensional world.
This is going to get annoying fast.
I love what this actually is better for some things, but I'm glad we didn't stick with this notation. So if I go out 2, 3 units, I'm sitting at 3, 180. It means the same thing as this negative sign. It's just an indication of direction. But you can think of these as being vectors. Okay? Direction and magnitude. Incidentally, we've now gone from describing things as sort of one-dimensional, here's my 0, to describing it in terms of distance from 0 and direction. So whether you use 0 or 180 or plus or minus, if you're going to have direction left and right, you are automatically moving from one-dimensional thinking to two-dimensional thinking. Even though you're on one number line, if you care which way you're going, you have distance from the origin and you have direction. So things are already a little bit weird. Now, addition and subtraction for these things is fairly straightforward. What is 5 plus -3? What's that equal? 2. Thank you, Diego. That wasn't meant to be a stumper. That should have been everyone in unison. So what do you think it means if I say 5, 0 degrees plus +3, 180 degrees? That would be kind of smart, but it's just, this says I'm 5 units, this is like a polar coordinate, except for only in one dimension. This says I'm 5 units from the origin, facing east, but I'm being told to go west 3 units. Where is that going to have me wind up? Same thing, but now we have to say 2, 0 degrees. 2 on the right side of the number line. Now, so this just means a change of direction. Okay, and these had better come out the same. If this notation is consistent, 5 plus -3 had better equal 2, whether we write it this way or this way. All of our math rules have to work the same. All right? Now, there's a couple of proofs of weird things you can do with vectors, and I'm not going to prove how. You're going to take my word on a couple of rules. Okay? That's the only part I'm not going to formally prove for you today. We studied 2 ways to multiply vectors. Do you remember what they were?
Dot product.
And?
Cross product.
Great, Diego. Thank you. Dot product and cross product. Dot product was this weird thing where you multiplied 2 vectors and got a number. Cross product was this weird thing where you multiplied 2 vectors and you created this 3rd-dimensional vector coming out of it. And stuff's crazy. We never just talked about multiplying vectors. I mean, what is multiplication with numbers? Multiplication is repeated addition, right? 3 times 2 is taking 2 plus 2 plus 2. You add 2 to itself 3 times. We never talked about what that would look like with vectors if you just added them multiple times. Well, it turns out what you get if you keep adding vectors. But there's a form of vector multiplication which in this notation would look like this. If you have one number and one angle, actually I'll use alpha and beta, and if you multiply that times another number and its angle, now we've only talked about 0 and 180, what you get is the product of the numbers and the sum of the angles. This does come up later. This is a general rule of just how to multiply vectors. Why don't we teach this before dot product and cross product? Because honestly, this is pretty useless. In physics, there are many, many uses for the dot product and even more for the cross product. There's not a lot of use for this, so we don't teach it to you. But if you just want to multiply vectors represented this way, this is how it would happen. There is a use for this in what we're going to do. So if I'm multiplying 2 things where I'm talking sort of 2 almost polar coordinates in a way, I would multiply the amounts and I would add the angles. Any questions on that rule? All right, let's see how that plays out on our number line. What is 2 times 2?
4.
Thank you. All right. By this system, positive 2 is 2 0 degrees, and I'm multiplying it by another positive 2 0 degrees. I multiply the amounts. 2 times 2 is 4. 0 plus 0 is 0. So does this system of notation work with what you've been taught all your life about multiplication so far?
Yeah.
So far by this one example. This isn't a formal proof, but let's try something a little crazier. What's 3 0 times 2 180. Now remember, if we're staying to one number line, 0 and 180 should be the only possibilities, right? 6, 0 plus 180 is 180. By the way, I have worked out the formal proof of this rule myself. It's not worth our time here, but I was not going to just take anybody's word for any step of this. Because it has honestly bothered me since I was around 11 years old that a negative times a negative equal to positive, and no one could really tell me why.
That bothers me too.
Hopefully this will bother you less then. You're going to have to take my word on this part. And if you want, we can you and I meet later, and I can drag you through this proof. It's kind of fun. Okay. So now, let's test that. What's 3 180 times 2 180? Now, in our old notation, in our notation that we're used to, this would be -3 times -2, right?
Yeah.
What do you expect that to be? 6. Okay. Multiply the distances.
60.
Yep, add the angles, 360 degrees. Now, the only two possibilities we originally talked about weren't positive and negative. They were 0 and 180, but where do we know 360 degrees should land us?
0.
Back to 0. So as long as you accept this rule, which I didn't accept, I proved, then a negative times a negative is a positive because 3 comma 180 times 2 comma 180 gets you 6 comma 360. Takes you back the way you came. That's the demonstration of it. It's all just direction. Positive and negative are just an easier notation than this to signify which way you were facing. But this is the real reason why multiplication with positives and negatives behaves the way it does. Multiplication, I just said a moment ago, is repeated addition. What do we call repeated multiplication? Exponents, raising to a power. Now, half of you went like this, indicating little exponents in the air. That was kind of funny. All right, I want to keep that rule up here. I want to keep that number line. May I erase everything else? Okay. Exponents, turns out, when you move up, exponents follows a rule kind of like this one, but everything moves up a notch on your sort of order of operations here. What I mean by that is, if I have a comma alpha, and I raise it to the nth power, for multiplication, we multiplied the lengths and we added the angles. You know how addition is kind of one rank below multiplication in the order of operations? Well, when you're raising one of these crazy numbers to a power, what you get, you can kind of distribute it. You raise the number to the power, but you multiply the exponent times the angle. Let's see if this works. What should, let's do an example here. What should 2 cubed equal? Not a stumper, yes? Wait, do you have a question on this, Danny?
Oh no, I just, yeah, that.
Okay, thank you for, yeah, you were about to tell me I didn't put that parenthesis in, thank you. What would 2 cubed be? 8. Okay, let's follow this rule now. 2 comma 0 degrees, gentlemen, to the third power. By this rule, that's 2 cubed and 3 times 0 degrees, which gets me 8 comma 0 degrees. Is that the same thing as positive 8?
Yeah.
Okay, good. This rule seems to be consistent so far. All right. Any questions on this? Going once, going twice.
It's actually kind of easy if you.
Yeah, if you buy that rule, it's not hard. I'm glad you think that way. We're going to do more with this later, but in a weirder way.
Wait, is that alpha plus beta? Is that plus or?
That's alpha plus beta, yes.
Okay.
All right. Let me do another example of this. Let's test how it works with negatives. What is -2 cubed?
This is another example.
Another example, thank you. Yes. What is -2 cubed? -8. Because you get a negative times a negative, which makes a positive, and then another negative makes a negative. 2 times 2 times 2 is 8. Let's do this with our rules. There's no negatives under this notation. there's 2 times 180 degrees. Raise that to the third power, and my rule says, this rule, says it's 2 cubed, comma, 3 times 180. And that's 8, comma, what is 3 times 180? 360 plus another 180?
540.
540. Figured somebody here who did gymnastics, stabbing, or skateboarding would know that. Which way does, okay, we've only started talking about 0 and 180. We've also had 360 degrees pop up here. Which way does 540 face?
No.
That way. Tim is pointing this way. Negative. So 180 and 540 are the same thing. So is this the same thing as negative 8?
Yeah.
Same direction, same distance, I'll take it. So it looks like our rule works. Turns out this rule works as well for fractional exponents. What do fractional exponents represent? Yeah, if it's 1, it's just being rooted. So yeah, okay, good. So what is, so let's see, 25, comma 0 to the 1/2 means 25 to the 1/2 power, comma 1/2 times 0 degrees. What's 25 to the 1/2?
So that would be 25.
What's the square root of 25?
5.
5. So that'd be 5, comma 0. That's positive 5. Now here we run into a slight problem with that some of you may notice. Is 5 the only answer to the square root of 25?
No.
No, it should be plus or minus 5.
Yeah.
Why don't I have a plus or minus option here?
Because the 0 makes you go to the
Right.
right, and you have to have 180 to go to the left.
Let's hold that thought. What is the square root of 25, 360? Well, let's see. According to my rule, that's going to be 25 to the 1/2 power, comma 1/2 times 360 degrees. What's the square root of 25? 5. There are no negatives in this system. What's half of 360? Huh. This is a slight inconvenience of this notation. Whether or not the square root of 25 is positive 5 under our notational system, or negative 5 under our notational system, 5, comma 0 or 5, comma 180, depends on whether you think you started over here at 0 degrees or 360 degrees. Now, if you're just standing here, if I just say, is this point at 0 or 360 degrees, is there a big difference between the two?
No.
No, except it turns out by this rule, here's 4, right? I could write this as 4, comma 0, 4, comma 360. Except it turns out that the square root of 4, comma 0 is 2, comma 0. And the square root of 4, comma 360 is 2, comma 180. So whether you got positive 2 or negative 2 as a root depends on whether you think you started at 0 degrees or 360s. It actually makes a difference how you got there now. This system's starting to look a little bit less convenient.
Yeah. A lot less convenient.
A lot less convenient. Well, if you accept this rule and that this rule leads to the exponent rule that I gave you, there's a conclusion that comes very obviously out of this system.
A third rule.
That, pardon?
A third rule.
No, it's the same rule. It's the exact same rule. But from just these two rules, there's a conclusion that is painfully obvious under this system and doesn't exist and is not at all obvious under the system you grew up with. This is what I'm about to show you is really the only reason to learn this old system. It's why it fell out of favor, to the point where a lot of mathematicians and physicists who use I every day don't know about this system, and that's where it came from. Under this system, this point right here, 1, comma 180, what is the square root, this is my 1/2 exponent notation, what is the square root of 1 comma 180?
190.
190. It's
1
1 to the 1/2, comma, 1/2 times 180.
And that puts you on a completely different thing.
Different thing, yeah. I was wondering what word you were going to use. Puts you on a different axis. In other words, once you include direction, you're already thinking two-dimensionally. Even if you think you're just thinking left and right on a one-dimensional line, you've added something that logically has to take you off that line. Suddenly, we have no choice by our own rules, and I ask you to take my word on that one, that we have to jump from here and rotate up out of this number line. And we get this point 1 comma 90. If we had decided to take the square root of 1 comma 540, half of that would have taken us down here. The square root of 1 comma 540 would have placed us down here at 1 comma 270. Yeah, remember there are no negative numbers here. There's just which direction you're going in. What do you think happens with cube roots? Yeah, but if you...
45.
Well, hold on. If you do a cube root, let's do one. The cube root of 1, let's keep the numbers simple. New example. The cube root of 1 comma 0 should be fairly simple. It's 1 to the 1/3 power, comma, 1/3 times 0, right? So that's just 1. Cube root of 1 is 1/3. Cube root of 1 is 1, sorry. And going in the 0 direction, that's just positive 1, no problem. What's the cube root of negative 1 under this system? Well, once again, we raise 1 to the 1/3 power, multiply 1/3 times 180, what do we get? 60. 1 comma 60 degrees. So the cube root of negative 1 is up here on sort of an imaginary unit circle. But once you introduce the idea of left and right, positive and negative, whether you know it or not, you've turned numbers into vectors. Once you're turning numbers into vectors, or a sort of different sort of polar coordinate, rules like this start applying. And once those rules kick in, it's actually impossible to stay on one dimension. So the cube roots and square roots of negative, well, the cube roots of negative numbers are fine. By the way, that you weren't taught that the cube root of negative 1 was out here somewhere. You were taught that it was just negative 1. Turns out it has multiple answers. We'll learn that a little bit later. But if you look at negative numbers as 0, and negative and positive numbers as 180 or 0 degrees, things like 1 comma 90 have to exist. You have to leap off of that number line. Logic insists that you have to go full two-dimensional. You can't just go partway two-dimensional. You can't just say left and right. You have to go left, right, up, and down. These numbers must exist. Now, lots of things exist in math that we don't bother to teach you because they're useless. Why? Anyone have any idea why we throw these things at you?
Because they're not useless.
Very general and accurate answer, Danny. Yes, they are not useless. It turns out if you're talking about anything, what I really does is rotates your way of thinking 90 degrees. It gives you an extra perpendicular parameter to play around with. When I first started teaching, I asked my dad if he ever used I. He was a nuclear physicist in the Department of Defense. So did you ever use I square root of negative 1 in your work? He said every single day for many years. He worked on the design of submarine hulls. What is always happening to a submarine hull when it's underwater?
Pressure.
Put under pressure. That pressure is always perpendicular to every point of the hull that it's pushing on. Turns out the square root of negative 1 can be used to represent that. No, I'm not doing an example that complicated. I'm not doing an example at all, actually. I'm going to leave you this thought. One other thought. When you run current through a wire, it creates a magnetic field that goes perpendicular out from the wire in all directions. Electrical engineers use the square root of negative 1 every day and for no reason that I know of, they call it j. I'm not sure if they still do that. If you find an old engineering textbook, it will have j equal to the square root of negative 1 instead of I. That made taking engineering and math classes together fun in college. I have to keep track of which number it was. So these imaginary numbers that seem so silly in Algebra 2, one, they have to exist. Once you introduce left and right, you've created a two-dimensional situation. And if you've created a two-dimensional situation, you can't just hang out on that number line. You have to expand into what we call I territory. We should call it that. We call it the complex plane. It. The IT, yeah. Ix, the IX plane. It is just called the complex plane, and these are rightfully called complex numbers. Points, why do we teach this now in the middle of what we're doing? Last year, you should have done some work with things like, I don't know, a point that maybe was 3 plus 2i. Does that look familiar from last year in Algebra 2?
Yeah.
Okay. This is sort of similar to the xy coordinate 3, 2. This is the rectangular representation. Tomorrow we'll go into more detail on the rectangular representation of points on the plane. This is the polar representation of complex points. We've been doing polar coordinates, right? So we are going to do rectangular imaginary numbers, as you used to calling them, though they're not really, as a review. And then either end of tomorrow or Monday, we are going to start talking about polar imaginary numbers. How do you represent this point, but in terms of its distance from the origin and theta? But they have to exist. Calling them imaginary is a disservice. They're as real as any other number. They're as useful as any other number, more so if you're looking at all-encompassing forces or magnetic fields. And they really exist. Any questions on why, if you're going to have negative numbers, you have to have complex numbers 90 degrees off that number line? Going once? Going twice? Nope. All right, we did that a little faster than I thought. We'll go over last night's homework for a few minutes.